Hey everyone, this is Big Brother Engineer and welcome to today's presentation on the conservation equations used in CFD. In today's talk we're going to go through the derivation of the conservation of mass and momentum and talk about the governing equations for an incompressible 3D fluid. In my last video about getting started with CFD, I mentioned that these conservation equations are very important for understanding what level of detail you need to solve your CFD software in and for understanding what's going on under the hood in CFD. So I think you're going to find today's presentation really useful. So without further ado, let's begin. So we start off by considering a fluid element at the macroscopic level, which means that the fluid properties are governed by macroscopic properties such as pressure, temperature, velocity, and it's big enough to neglect molecular properties. So we have our macroscopic fluid element here, sort of a fluid parcel, if you will. And we know in this fluid parcel that mass is conserved, energy is conserved, and momentum is conserved. And these are from observing the world around us. We know if we have 5 kilograms of fluid and we put it in one end of a pipe, we should get 5 kilograms of fluid leaving that pipe. That's conservation of mass. Mass will not be created or destroyed in our fluid element. We also know that momentum is conserved and that it follows Newton's second law. So all the forces applied on this fluid element is equal to the rate of change of momentum, F equals ma. And we also know that energy is conserved in our fluid element. So this comes from the first law of thermodynamics, that energy is never created or destroyed, only changed from one form to another. So from physics and from knowing the laws of physics that govern the world around us, and we know that these must hold true for our fluid element, and using that we can derive the conservation equations for our fluid element. I've also denoted each of the sides here, delta z, delta x, and delta y, in correspondence to this coordinate system here. So before going through the conservation equations, I think it's useful to go through a revision of a Taylor series expansion, as it's used quite often in the conservation equations. And what a Taylor series expansion does is it lets us approximate a quantity at another point in relation to a point that we know. So for example, if we know the pressure at the east face, we can use a Taylor series expansion to determine the pressure at the west face. And since we know for our fluid element here that it's very, very small, we can neglect the higher order terms of a Taylor series expansion and use just a linear part of the Taylor series expansion. So if I know the pressure at the cell center here, or at the fluid element center, and I want to determine the pressure at the west face, I can describe a Taylor series expansion between the west face and the center, and I can neglect the higher order terms of the Taylor series expansion and use a linear approximation. So the pressure at the west face will be described as P, which is the pressure at the center, plus dP dx times the distance between the cell center and the west face, which in this case would be a half this distance here, delta x. So the pressure at the west face can be described as P plus dP dx times a half delta x. This is essentially P plus the derivative times the distance. And the pressure at the east face similarly can be described as the pressure at the center, and then the derivative would be minus dP dx, and then the distance will be a half delta x. So this linear Taylor series expansion can be used to describe the pressure at the west face and the east face in terms of the cell center. And what we're essentially doing here is we're drawing a straight line between the west face and the center, and saying that we can use pretty much a linear approximation to estimate the pressure at the east and the west face, due to the fact that our element is so small. So this is how we use a Taylor series expansion in our conservation equations. I also have here that this holds for any quantity such as velocity, pressure, temperature, etc. So that's quite important, and we'll use it quite often in our derivation. So for the conservation of mass, since we know in our fluid element here that no mass can be created or destroyed, we know that if there is an increase in mass in time, that has to equal to the mass that increased or decreased through the phases. So this right here is essentially a statement of the conservation of mass. If we have any increase in mass in time, that has to equal to the increase/decrease through the phases. Mass cannot be created or destroyed in our fluid element. So determining an expression then for the increase of mass in time, that's simply equal to m dot, or dm dt, partial m dt, partial m partial t I should say. And since we know that the mass of the fluid element is simply equal to rho v, we can substitute that into our equation. And then since we know the volume of our fluid element here is delta x, delta y, delta z, we can sub that in for our volume. And this gives us an expression for the increase of mass or decrease of mass in time. Now all we have left to do is determine what the increase or decrease of mass through the faces are. And this is where we can use our Taylor series expansion to help us. So we know that the mass, let's take a look at just the x direction and the east face first for an example. And we know the mass entering the east face here in this example here, where we have velocity in the x direction, is equal to rho VA. And this comes from fundamental fluid mechanics. If you haven't used too much fluid mechanics before, I've put a unit check here to show you that we do in fact get kilograms per second by using this formula, but nonetheless we can describe the rate of change of mass through the east face as rho v times the area in which it flows through. And knowing that the area of this face here is equal to delta z delta y, we can substitute that into our equation. And also we know that the velocity at the east face is equal to the velocity at the cell center minus partial u partial x times a half delta x. And this comes from the Taylor series expansion that I showed in a couple of slides back. So that's how we can determine the velocity at the east face in terms of the velocity at the center here. So substituting that expression in here for our velocity, then we arrive at this final expression here for the velocity entering the east face. And to determine for the mass rate of change entering the east face, I should say. And to determine the mass leaving the west face, we follow a similar development where we use u plus partial x this time times a half delta x for our Taylor series expansion. And again, we use the same area, delta z, delta y. So following this process then for every face of our fluid element and summing them all together, where we use a plus sign for mass coming into our fluid element and a minus sign for mass leaving our fluid element, we can come up with this expression here for the total rate of change of mass of our fluid element due to fluid coming in and out of our fluid faces. So this is due to the mass entering or leaving the fluid faces. And after using some factorization here, this is the final expression that we come up with in red for the total mass entering / leaving the faces. And we said before that for mass not to be created or destroyed in our fluid element, we know that the increase in mass in time has to be equal to the increase or decrease of mass through the faces. So we let our previous expression, partial rho partial t, dx dy dz, delta x delta y delta z, equal to the expression we just came up here for our increase / decrease through the faces. And noticing here that we have delta x, delta y, delta z on both the left and the right hand side, we can cancel that out. And this gives us our final expression here for our conservation of mass. And this is known as the continuity equation. And this is our generalized form for the continuity equation for fluids and gases. But there are some more simplifications that can be made. So if we have steady flow, you'll notice that we can neglect the time rate of change term. So this becomes our steady flow continuity equation. And if we have an incompressible flow where there's no change in density, this is what the continuity equation would look like for a steady incompressible flow. So this is our conservation of mass. So from vector calculus, we know that the del operator is equal to delta x, delta y, and delta z respectively in the I, j, and k directions. So we can use this to greatly simplify our continuity equation shown here by simply replacing these partial derivatives here in the spatial directions as del dot rho v. And this is just a more compact form of the continuity equation that you may see in textbooks or online. And this expression here is the continuity equation for a steady incompressible fluid, which is equivalent to this expression here. So this is just a simply more compact form of writing the continuity equation. Now I've also put some more terms on screen to represent what's often used in vector calculus to simplify partial derivative terms, and I'd encourage you to keep an eye out for these trends in our conservation equations, because these are often used in fluid mechanics to simplify the equations. So whenever we have this pattern here often del Q is used, and whenever we have this pattern here, often del dot Q is used. So I'd encourage you just to keep an eye out for these trends in our conservation equations, as we can then use these smaller terms to simplify our expressions. So for the conservation of momentum, we know that the sum of the forces acting on our fluid element has to equal to the rate of change of momentum. So the sum of the forces has to equal to the rate of change of momentum, where this capital D ddt here is the total derivative. And the total derivative represents the rate of change of a quantity with respect to time and with respect to space. So if I have a look at the rate of change of momentum expression here, which is the material derivative or the total derivative, that's equal to the rate of change of momentum with time plus the rate of change of momentum in the x direction times the u component times the rate of change in the y times the v component plus the rate of change in the z times the w component, the z component of velocity. So this ddt term is the material or total derivative of a quantity, and essentially what it does is it takes into account the change of a quantity in time and space. So this is what's often called the total derivative in vector calculus. So we'll use this simplified expression here with the capital D dt to talk about the rate of change of momentum. But just note that this ddt is not simply a derivative with respect to one direction like partial derivatives would be. It actually is this much longer expression here. So the rate of change of momentum we can write as the total derivative of m times v, and of course we can write the mass as rho v, and then writing the volume in terms of delta x, delta y, delta z, we get this final red expression here for the rate of change of momentum. Now, with the rate of change of momentum determined, all we have to determine now is the sum of the forces acting on our fluid element, and let it equal to this red expression here for the total rate of change of momentum, and that will give us our conservation of momentum equation. So calculating the sum of the forces on our fluid element, then we have two sets of forces acting on our fluid element. We have body forces and we have surface forces, where the surface forces are equal to viscous forces and pressure forces. So let's consider the x direction only just to simplify things. The body forces in the x direction, that's equal to forces such as a centrifugal force, a gravity force, an electromagnetic force. We're going to neglect all body forces here except for the gravity force. So we're going to say that the total body forces in the x direction is equal to any gravitational component in the x direction here. So that's the total body forces in the x direction. So with the body forces determined, now we just have to determine the surface forces, which is equal to the pressure forces and the viscous forces. So taking a look at the pressure forces in the x direction only, we have a pressure force at the east face, which is equal to the pressure times the area. So the pressure at the east face is given by this expression here from our Taylor series expansion times delta z delta y, and the pressure at the west face is given by this expression here times delta y delta z. So summing these forces up, where we have this expression here for the pressure force at the east face and a negative sign here to indicate that the pressure at the west face acts in the right to left direction. This is the pressure at the west face, and summing these two terms up, we get minus partial p partial x delta y delta z for the total pressure force acting in the x direction. So now we just have to determine the viscous forces acting on our fluid element, and that can be determined from the viscous stresses. Now unfortunately the viscous stresses are a little bit more complicated to describe, because we at a singular point there are 9 components of the viscous stress, and this is known as the Cauchy stress tensor. If you'd like to learn a little bit more information about this, you can simply search up the Cauchy stress tensor. But I can describe the subscripts of these terms here to help you understand a little bit more where these terms come from. So taking a look at one component here, the tau xy component, the first subscript indicates the surface which the force acts, and the second component indicates the direction in which it acts. So since the first component here is x, that describes that the viscous stress here acts at a surface normal to the x direction. So if you have a look at the x direction here, you can see that these three terms here all have x as their first subscript. That means they act on the surface which is normal to the x direction. So that's what this first subscript indicates. And then the second subscript indicates that the direction in which the stress acts. So you can see the second subscript here is x, so that means that it's going to act in the x direction. This one here is y, it acts in the y direction, and this one here is z, so it acts in the upwards direction, or the z direction here. So the first subscript tells you the surface on which the force acts. So with the subscript being x here, it acts on a surface normal to the x direction. With the first subscript being z here, it acts on a surface being normal to the z direction. Similarly for the y. And the second subscript indicates the direction in which that stress acts, as seen on screen also. So this is how we describe the viscous stresses acting on our fluid element. Now, if we know the viscous stresses acting on the element, then we can determine the viscous forces by simply multiplying the stress by the area, right? And taking a look at the viscous stresses in the x direction only, we have to take into account all terms which have x as their second subscript, as this indicates the direction. And let's take a look at the terms of the viscous forces acting in the x direction. So at this east face here, we have this viscous stress term acting, and we take this viscous stress multiplied by the area, delta z, delta y, and that gives us this first term here, where I have a negative here to indicate the fact that it's acting from right to left. And similarly, we have a viscous stress at the west face, which is equal to this term here, which appears here, times delta y, delta z, which is the area. And I do this for every face, and this is the final expression then that I get for the total viscous forces acting in the x direction. So this is our viscous stresses multiplied by the area of the face on which they act, and that gives us the total viscous forces in the x direction. So firstly, we determine what the rate of change of momentum was from the material derivative, and we figured out what the total forces acting on our fluid element were by summing up the body forces, viscous forces, and the surface forces. Now we can substitute all of these expressions into our equation for our Newton's second law, and we can determine the conservation of momentum. So I've highlighted each term here in different colors just to make the visualization a little bit easier here. So considering the conservation of momentum in the x direction only, we have the pressure forces here in green substituted into the equation here. We have the viscous forces here and the body forces here, and this is the sum of the forces. And we let this equal to the rate of change of momentum. And after some rearranging and cancelling out of delta x, delta y, and delta z, this gives us our final expression here for the conservation of momentum in the x direction. A similar process can be applied in the y direction, and we get a quite similar expression then for the conservation of momentum in the y direction, and similar in the z direction. And I will leave it as an exercise for the viewer to go through and make sure that the conservation of momentum in the z and the y directions is in fact equal to what I have shown on screen. And I have indicated all of the force terms here, so you can go through the same process of simply summing up all the forces and letting it equal to the rate of change of momentum and cancelling out some terms, doing some factorizations, and you should end up with this expression here for the conservation of momentum in the z direction. So here's the final general form for the conservation of momentum equations for our fluid element. Now, with our conservation of momentum equations determined, we have now introduced some extra unknown terms here via our viscous stresses. So we need to determine what these viscous stresses are in order to solve the equations. And this is what the Navier Stokes equations do. By subbing in an expression for the viscous stress in terms of Newton's law of viscosity, we can write our expressions in terms of velocity components only. So Newton's law of viscosity states that for a Newtonian fluid, the viscous stress is proportional to the rate of shear strain. So this is the equation you may have seen before from fundamental fluid mechanics courses, that tau xy is proportional to the rate of shear strain, which is this partial u partial y plus partial v partial x, simply multiplied then by the dynamic viscosity. And similarly for the shear strain terms in the zy and xz directions, we can write the expressions as such. Now the normal stress terms are quite similar. insofar as we have a term here which is 2 mu times partial u partial x, which is essentially the strain term, and then we have this extra term here minus 2/3 mu del dot v, which is a secondary small viscosity term, and that's added to the end. So the main takeaway from this slide is that we can relate the stress terms in terms of velocity terms only. So if you have a look at all the expressions here, we have just the velocity components in here, so we can now substitute that back into our conservation of momentum equations and attempt to solve the equations. And this gives us our most general form for the Navier Stokes equations, where we substitute our shear stress terms with Newton's law of viscosity, and these are the resulting set of equations once we do so. And as we look at these equations, we can see that there are some problems in order to solve these equations, since we have 3 equations here and 4 unknowns. And the problem comes in the fact that we have all of our unknown velocity terms here, u, v, and w, but the problem comes by the fact that we have our pressure term here as well. So we have no explicit term for pressure, which means that these equations can't be solved alone. For an incompressible fluid, however, we can make some simplifications, and since we know that del dot v is equal to 0 from continuity that I shown in the conservation of mass, we can cancel that term out. Taking the x momentum equation then and going through purely mathematics, we can make some more factorizations and simplifications for an incompressible fluid and determine that this is the x momentum in the x direction. I'll leave it as an exercise to the viewer to pause the video and take a look at the mathematics I've done to get from this expression down to this expression in red and determine that they are in fact equal. So when I make these simplifications in the x, y, and z directions, this is the final resulting set of equations, and these are the Navier Stokes equations which govern the motion of a 3D incompressible Newtonian fluid. And as I said before, these cannot be solved alone. They have 3 equations and 4 unknowns. So this is generally coupled with the continuity equation in order to solve, but there are still issues with solving these equations, and this is due to the fact that we have non-linear terms in all 3 of these equations here, which means that it's quite difficult to solve. And also the continuity equation is not really an equation to solve, it's more of a restriction on the solution. So due to this fact, it's actually quite difficult to solve these equations for a fluid flow. Solving the conservation equations usually requires an iterative approach. So what we do in CFD is in fact we provide an initial solution to these equations, and once we have an initial solution we can iterate until continuity is satisfied and we have our final solution then. And this is what's done in the simple and the piezo algorithm. When you're in your CFD software and you click initialize, what you're doing is you're setting an initial value for velocity and pressure in each of the cells. And what the simple and piezo algorithm does is it iterates through, ensures, it checks if continuity is satisfied, it iterates through solution, and until eventually continuity is satisfied. And that's what's done by your CFD code when you're solving your CFD solution. And again, you might see the conservation equations wrote in this simplified form, where we use the del operator here just to simplify everything just a little bit further into more compact form. And you can see the usefulness in using the del operator here, as the equations are much more compact and much easier to comprehend. So I've just left a reference textbook there for anyone that's interested in taking a deeper dive into the derivation of these conservation equations. I hope you enjoyed this video, and let me know in the comments what your thoughts were, and yeah, I'll see you in the next one.